Warm greetings to everyone. Today we are going to see about the strain energy stored due to bending or the bending moment. The bending moment is denoted by capital M and the strain energy is denoted by capital U. So if you apply a load on a given beam, it is going to bend, which produces the shear force at bending moment in the beams, whether it is a cantilever or a continuous beam, or in the case of fixed beam, or a simply supported beam or a proper cantilever beam. So now we are going to see about the bending moment on a simply supported beam which is loaded with an UDL which is of W per meter run over the entire span of the beam, and the span of the beam is capital L. You know that due to axial load, the strain energy stored can be determined by using the equation capital U is equal to P square L divided by 2A into E. Already I have dealt in the previous video lecture. So now we are going to see only about the strain energy stored due to the bending in the beams. So since it is a simply supported beam with the UDL throughout the span, so it is symmetrically loaded beam. So due to the symmetry, the left part will be of A and the center will be of capital C and the right end of beam is capital B. So you can have the mirror image of first part as well as the second part of the beam AC and CB. And you know that I am taking the first portion AC. I am having a section XX in the AC portion which is at a distance of small x from the left support A. So the moment due to the given reaction and the UDL is, you know that reaction is WL by 2 on either side of the support. So the bending moment Mx is equal to WL by 2 into X minus load intensity, UDL load intensity small w into X square by 2. So WL by 2X minus small w X square by 2. So that is the moment at the section XX which is at a distance small x from the left support. Now you know that the strain energy stored due to the bending is denoted by capital U, that is equal to integral of 0 to x, where 0 is the lower limit and x is the upper limit, that is x is equal to 0 to x is equal to L by 2 into m square x, where mx is the bending moment section xx, mx square into dx divided by 2ei, where ei is the fluxural rigidity of the beam. So if it is a rectangular beam, the moment of inertia is b into d cube by 12, which is of width b and depth d, and e is the Young's modulus of the material of the beam. So if you know E and I, you multiply it, you will get the fluxural rigidity in terms of kilonewton meter square or Newton into millimeter square. Then you substitute in the equation, right? U total strain energy stored capital U is equal to integral of 0 to L by 2 into, I am substituting the mx value, that is WL by 2 into x minus WX square by 2 the whole square divided by 2ei into dx. So that is the energy stored for one region AC. So since it is symmetrical, you multiply by 2. So that is 2 into integral of x is equal to 0 to x is equal to L by 2, right? WL by 2 into x minus WX square by 2 the whole square into dx divided by 2ei. So you can simplify this equation, you can get the corresponding strain energy stored. And also you know that strain energy stored capital U is equal to the product of the force into deformation, the direction of the applied load. So that is equal to, right, capital W by 2 into delta, where delta is the deformation. So half W by half W into delta. So W by 2 into delta. If you are equating the work done is equal to energy stored, you can get the value of the deflection, because already you know the total energy stored. That's why we have that's now we have solved it, and you equate to the work done, that is W by 2 into delta. So you can get the deformation or the deflection of the beam. You know that the symmetrically loaded beam of simply supported with the UDL throughout the span L. So you are having a symmetrically loaded beam. That's why the maximum deflection always occurs at the midpoint. So the deflection for a simply supported beam with the UDL throughout the beam. So you know that phi WL per 4 by 384 EI, where small w is the intensity of UDL and L is the span of the beam and EA is the fluctual rigidity of the beam. Based on the cross section of the beam, definitely you can get the fluctual rigidity of the beam. So the delta you can get in terms of the meter or millimeter or centimeter. So this is how the strain is stored and the deflection on the beam, whether it is a simply supported or cantilever or the fixed beam, or in the case of a overhanging beam, either single or double overhanging beam, you can solve the problem. So this is in terms of the notation I've used. Similarly, you can solve the problem using the total energy stored and the deformation required on a beam by means of analytical way also. So thank you very much for patient listening. In the next video, we can see the numerical problem in the case of strain G stored and the deformation of a given beam. Thank you very much. Welcome, Vijayam. Welcome,